Hi everyone, I'm Lukas, I'm working at Tilebox, and we are building a space data native tool to hopefully make all of your lives a little bit easier. Earlier I already had a talk where I showcased off our datasets module, which essentially is a managed metadata catalog, and the second part of our tooling actually is a workflow orchestrator, and that's what I'm talking about today. So I know what you might be thinking, like workflow orchestrators are not a new thing. I already use Airflow. Why would I ever want to switch? And I'll get to that in a bit, but basically I want to define quickly what I mean when I talk about a workflow orchestrator, which means typically you talk about splitting up your work into smaller granular tasks that you want to execute in some sequence, and what you get from this typically is like a tree of relations in which tasks are related to each other. Like one task can spawn more tasks that compute additional work and so on. And you end up with this concept of a DAG, the directed acyclic graph, which comes up a lot in workflow orchestrators. And you have here like an illustration of what that can look like. Now, the thing about our workflow orchestrator, we really try a lot to get out of your way and not be a whole platform and mindset you have to really operate in. We just want to be the tool that facilitates your work. And something that drives this home quite well is the situation. I've seen it a lot, and I'm certainly guilty of this myself. You start building your algorithm. You start working locally, it's just a bit easier for development, right? You download your granules. You have your nice Jupyter notebook that's running your algorithm on some images. You download it, and everything's working great. So now I want to do the same, but on a global scale. And yeah, I mean, I already have all the algorithm, and it's easy. I just deploy it and be done with it. But often times you realize this last step of going from my working prototype in the notebook to the production grade system, that's way more work than originally anticipated. But I believe it doesn't really have to be. And the way we go about this is right from the get-go, you start prototyping also your algorithm and splitting up all your work into this granular concept of tasks. Typically, you would write and structure it into functions, and instead, when using this tool, you instead convert this into tasks that essentially are really similar to functions. And they do have one additional advantage, which is one task can spawn and submit another task, a subtask, and it can set up dependencies between tasks, meaning this task only can run after another one has already been computed. So if you do that, then you have the ability that some user comes along and initializes your tasks with some arguments and submits it as this is something that should be executed. Please execute it for me. If this request comes in, nothing is going to happen unless you have some kind of execution agent executing your tasks. And that's what we call a task runner, which basically just means this task you implemented, wrap it up into a script, make it executable, and that's how you get a task runner. And with just one task runner, you haven't gained very much yet. Like we can take a look at the DAG of like one sample workflow that you can execute. And with one task runner, it will just pick an open task that doesn't have any outstanding dependencies. It will execute it. It will pick the next task, and so on. And at some point, now you have the whole workflow done. Sequentially, you haven't really gained much of this yet. However, if you look at the stack, you already see that there is potential to parallelize this, right? So all of these read region tasks in the bottom, they don't have dependencies on each other. And that's a theme a lot in spatial workflows with chunking and so on, that you have lots of tasks that operate the same algorithm on different regions, but without any interdependencies. And the way we can actually make this parallelize is we just start multiple of our task runners, right? This task runner is a Python script you start on a machine. And if we start 3 task runners, we don't have to modify our task code or anything at all. We just start multiple task runners. Then we submit another job. And what you'll realize is, if you take a look at the DAG now, all of these 3 are executing in parallel. And once all of these 3 are done, there's then one of those will just get scheduled the 4th remaining processing task in this case, and the whole workflow could be speed up by throwing more compute at it without actually having to worrying about writing and implementing parallelization mechanisms. And all of this could be achieved by structuring your workflow from the get-go into this small concept of tasks. So the order in which tasks get executed is determined by our workflow orchestrator. The task runner just sends a request to the workflow orchestrator telling it, so this is the tasks that I can execute. Please give me some work to do, right? And the workflow orchestrator just answers, yeah, execute this. But it actually matters a lot how you go around as a workflow orchestrator, how you do the task scheduling. And what we have realized, it's really a good idea to always do this stepped first. So if a task just finished that spawns subtasks, always give this runner one of the subtasks if possible. And if no subtasks are, get a sibling next and then traverse the route up, because this, the way that data chunking typically looks like and works, you can get a lot of cache performance gains from this, because the same worker typically requests the same kind of chunks of data. So that's generally a really good idea. And there is another concept here, and we refer to this as work stealing, that actually comes from decentralized workflow orchestration, where you have a bunch of runners that each work separately on their own. And once one runner gets idle, it wants to perform work, so it talks to other runners and essentially stealing their work. And that's a concept we adapted here as well. And what allows this to do us is, if you have an already ongoing workflow with one runner, like we have at the moment, at any point of this, I can start up another runner, like while the workflow is running. And this runner, it wants to execute tasks. So now it's essentially stealing work from what the original runner generated. And at this point, you always want to return the task that's like the highest up in the tree. So here you do the actual, not the depth first version, but you go breadth first with work stealing. And obviously, you can't only start up one runner, but you can start up multiple. So if another runner came available now, this is what our DAG would look like then. And this architecture alone already proves really powerful if you combine it with compute engines and autoscaling clusters. You can have one runner running on a compute engine, for example, and then you have some monitor on the CPU usage of it. So if users start submitting jobs, your runner will start active, and if the job volume increases, the runner's CPU usage will go up, right? Now your autoscaling kicks in, and just because of this metric, it starts up another runner. And this will immediately kick in, pick up work from the original task, and suddenly you have all of this parallelized. Obviously, with cloud compute, you can get quite crazy how many runners you really want to have. But as soon as the work dies down a bit again, you can scale down to just one runner, for example. So far, we always had users submitting jobs. That's basically the concept of batch processing. I really want to process this area now and want to see the results. A similar concept, which we use a lot, is related to near real-time processing, where you always want to react to external events. For example, when new data comes in, we want to process this right away. And in our architecture, this is just a different way of how a job is triggered. Instead of a user sending a request, we react to some external event. Now, something that's really useful and that we can utilize a lot of this architecture, that I want to showcase that for a small practical example. So this is what the typical workflow processing some satellite scenes could look like. basically processing some scenes over an area of interest. First, you have a step locating what data do you actually need. Then you read in that data, you regrid it to some aligned grid. Then you combine it, you aggregate it, you perform some analysis on it, and eventually you visualize it. And that's like the simplification of this. In reality, it will look more like this. Like many of those steps can be parallelized, right? And so far, we always started working locally. We downloaded some data, and the runners always had local access to the data, which can get you quite a lot. But now if you are talking about huge data sets, obviously this doesn't work anymore. So what you really want to do here is you always try to move your runners to the data whenever that is possible. And because runners, the execution agents in our case, you can move them around quite quickly. It's literally a Python script, a Docker container, whatever. So you always try to move it as close to the data as possible. And you can have runners working on the same workflows in different locations across execution environments. Like you could have one that has access to a GPU and another one that has access to a lot of data, and the data runner can submit subtasks that get executed on the GPU runner and so on. So you always try to move your runner to the data. That's like the core concept. Obviously, that's not something you can always do because not all data is like available in some object storage that also has compute capabilities. Then you often need to get a bit creative. Actually, a couple of years back, I worked on some larger Dropomi processings where we wanted to do global scale aerosol maps based off Dropomi data. We needed, I think, like 3 or 4 years of data for this. And that was, I think, half a petabyte of data scale already. It's a hyperspectral imager, right? So the way to access this back then, it didn't exist as an S3 bucket. So actually, that was part of an ESA project. So our creative solution there was we literally put the data from Esrin into a lot of hard disks, put it on a truck, shipped it to our compute runner in Vienna. That way, we ended up with, I think, a bandwidth of it was 500 terabyte in 12 hours, which if you calculate that down, it's like 70 gigabytes per minute, which actually is quite a good bandwidth. But yeah, now with Cloud Native, fortunately, we don't need to do that. We can even utilize this for the Dropomi workflow I described, because there's now one cloud offerer who actually has the big advantage that they offer all of the Sentinel data co-located to their compute. The big disadvantage here is their compute is quite expensive compared to like AWS or Google. So I don't recommend you move all your compute always to Cloudflare. That's probably not a good idea if you want to save on your compute bills. But what our architecture allows you to do, you rent one single VM on Cloudflare and keep all of your other compute as well. And then you split up your task runner into, so now you have one runner that's only capable of reading the regions and putting it in some storage. And you have other runners that actually do analysis on this data. And remember, you still didn't need to change your original tasks or implementation or code at all. This is just a matter of how you set up your execution environments and so on. And that way, what you get immediately is this architecture here. Sorry, that was one too much. So this architecture here, where you have a couple of task runners working on one environment, collaborating and submitting tasks to a task runner in a completely different environment, but that has the advantage of data access in this case. And we really design our orchestrator to be multi-cluster, multi-environment friendly, and we can take that one step further even with multi-environment. That also applies for in-orbit processing. It's been getting easier and easier, right, to build your own satellites, rent the spot on the next SpaceX launch, be up there in orbit. Then Amazon has this nice service called Ground Station. They basically put antennas on all of their data centers, so you can downlink your data from your satellite, via this ground station network, and it ends up in an S3 bucket. But if your satellite is a hyperspectral imager taking lots and lots of data, this downlink can be quite the bottleneck, and it's really expensive. So you really want to save bandwidth as much as possible. And one way to do that is to only downlink valuable data. And for many applications, you don't want any cloudy products at all, right? You immediately discard them for further processing. So it would be really cool if you could do like an initial filtering step already in orbit. So now you have one task that runs on the satellite in orbit, still as a task runner. Obviously, it won't talk to our API backend here on the Earth, but we have a standalone binary version of this backed by SQLite, and it offers exactly the same API. So our cloud runner, so our satellite runner talks to this. It processes the satellite imagery in orbit, puts it into a downlink folder if it actually makes sense to downlink this. Then it ends up in an S3 bucket. Here you can have an automation. It's like a trigger when new objects are available. This submits a job on the ground, and you immediately start processing and continue on from that. And so that's the essence of the idea of this multi-cluster environmental setup we have. I quickly want to showcase or mention some more features that are relevant for all workflow orchestrators. And of course, we also include, for example, retry handling. So far, it has always been smooth sailing. All the tasks always succeeded, but that's not often the case. And what you really want to have is an architecture where you have some issues in one of the tasks or even a bug, and you just fix the bug, update your task runner, deploy it again. Now you retry your job, and only this one failed task needs to be executed. Everything else is already done. You don't need to rerun everything. But with a lot of tools out there, that's unfortunately the state of what you have to do. Another cool feature we have included into our task runners is full observability. So you just add a little configure call when you start up your runner, and it will start collecting open telemetry traces and logs, and you can put it to some tool like your observability platform, and then you get full insight into like the task execution durations and log messages and so on. And this even works in orbit. So this standalone Tilebox workflow orchestrator we have in orbit has an open telemetry collector as well. So the in-orbit runners push their traces to that. It writes it into a downlink folder, it gets downlinked, and on the ground you can ingest it into your observability platform, and you get full insight into what happened in orbit, which is typically a very difficult challenge to solve. And so far I've always showed the Python side of things. We also are multi-language, so you can write, right now we support Go and Python, but more languages are planned in the future. You can write the workflow that has a Python runner and a Go runner, and the Go runner even can submit a task to the Python runner. It only needs to know what parameters this task needs. So in this example here, you just skip the actual execute method when you define the task in Go, because you know it will be executed by the Python runner. And that's pretty much for the features we have at the moment. But I wanted to share with you one idea that came up for us recently, especially when talking to the needs, like to our customers and their needs. And it's this one concept we call federated computing. And what I mean by this is this architecture that we have in mind, which allows you to run like scheduled workflows that have parts that run pretty much everywhere. You can have some algorithm providers that are really good at their algorithms. Like there's companies out there that have really nice cloud masks, for example, or that other companies that are really good at atmospheric correction. So now if I'm some new startup wanting to build my own satellite, I need all of those things, right? I don't want to spend my time implementing and working on all of these algorithms. So ideally, that's something I could just reuse. And with an architecture like this, you could actually offer federated computing. An algorithm provider provides like their hosted versions of their task runners, And customers can submit tasks to the runners of the federated computing providers that get executed there. They know the results will be written back in the same bucket that they put as input to the task. And then you just continue on, and you have this plug and play system where you can swap out different algorithms, add more to your pipeline, and so on. So this doesn't exist yet. It's a long-term goal of what we envision could happen. I would be really curious what you think of an architecture of this and what the challenges are to actually solve this. So if you have any inputs or ideas on this concept, then please feel free to reach out. I would be really curious to chat about that. So that's already it. So I didn't include a demo here to showcase all of this. Would probably have limited my timing talking about all of the concepts in between, but I really invite you to just check it out yourself. You can sign up for free, generate an API key, and then you can already start up your own runners. We have all of this documented as well, so all of the concepts I just talked about, it's really in detail there. And if you end up building some really nice workflows, then feel free to share them with us. I'm always curious to see what you can build. For example, I've recently started messing around with using this to have parallel writes into a SaaS store, because it's like already nicely chunked, and so are these task runners like completely working and separate, and you can end up writing to the same object storage, and it's actually a neat way of solving this parallelization problem there. Thank you.